Hello, everyone. Let me start by first sharing the screen. Takes a little bit time. Okay. So I would like to start by thanking my hosts, Professor Matos and Coelho, who have invited me to give this keynote lecture. And this is part of the workshop of integrated process and product design for sustainable biorefineries. I wish I could be present to give the lecture in person, but unfortunately it's not possible. My talk is about the challenges and opportunities for sustainable process synthesis design and analysis. I've divided my lecture into 6 parts. The first part is related to background knowledge in terms of multi-layered view of chemical and biochemical engineering, some definitions. I'm sure you're all experts in sustainability and sustainable design biorefineries, but I would just like to introduce my definition so we are clear about the references. In my view, the multi-layered that is the multi-layered view of chemical and biochemical engineering. To understand this, from left to right are the core activities that we perform. That means we convert resources to products and we produce wastes, and we need a process. And from bottom to top, in order to do these core activities, we need the fundamental principles of chemical and biochemical engineering, like thermodynamics, separations, reaction engineering, transport phenomena, and so on, so that we can design the process, we can control the process, we can operate the process. But is that enough? Because with respect to the resources, we also need to know demand and availability. With respect to the result, we need improved product and less waste. And if we achieve this, we will achieve the goal of sustainable technology. But in order to do that, we also need to augment the fundamental principles with a combination of science and engineering. But is that enough? Because we also need to look at the location, type, demand, availability, recovery of resources. We need to find not any improved product, the optimal product, lowest waste, control environmental impact, and so on. In order to achieve this, we also need to not just science and engineering, we also need integration of ideas, disciplines, data sources, and others, so that the ultimate goal of sustainable development can be achieved. So, and on the right, you see the specific contributions of chemical and biochemical engineers. So we can achieve these, give these contributions through this multi-layered view of chemical and biochemical engineering. Now let's define the synthesis, design, analysis problems. On the left-hand side, you can see a list of unit operations. The objective of process synthesis is to find the sequence of these operations that give us the product that we want from the raw materials that we can use. And what you see is a superstructure of different alternatives, and we want to find the best one. Once we have found the flow sheet, then we need to design the flow sheet in terms of adding more details to the operation, like in a separation column, the number of stages, in a reactor, the temperature, pressure to give the conversion, and so on. At the same time, once we have the design and the synthesis of the process, we also need to analyze to find out if there are any errors, if there are opportunities for improvement. And based on these, we can set new design targets. And if we can match or find alternatives that match these design targets, we would have an improved process. So very shortly, briefly, these are the synthesis, design, analysis problems. The product synthesis design analysis problems are also similar. Instead of unit operations, if we think of atoms and bonds and groups of atoms, we combine them to form molecules. Here are examples of molecules, and then we need the properties of these molecules to understand the behavior of the molecule or the product. We are talking about sustainability and sustainable development, so let us also look at the definition of sustainability. In my view, which I like very much, is the definition that says the ability to sustain or the capacity to endure changes is sustainability. We can also try to understand it from the figure on the left. On the y-axis is human progress, shown by the green curve going upwards, and on the x-axis is the time domain. And what we see is that at different periods of time, different technologies were developed, and before they became redundant, a new technology took over. And by having a sequence of these technologies coming and dying, we could sustain ourselves on Earth. So that is, in my view, the capacity to endure changes or sustain, the ability to sustain. What is sustainable development? Again, I like this definition, which says the development that meets the needs and aspirations of present without compromising the ability of future generations to meet their own needs. Question also is there time now for a new change in technology? Or which technology do we need in order to make a new jump and avoid break of the curve going downwards? With that definition, let us look at the challenges that we are facing. On Earth, we have a number of resources. Some of them are shown here, but these resources are not uniformly distributed. As we have already stated, one of the main goals of chemical and biochemical engineering is to convert the resources to the products that we need to sustain ourselves on Earth. And these products need to be continuously improved and updated. So the challenge, how to define the products to make, identify the raw materials that can be used, find the processes that can manufacture the product in a sustainable manner. Another challenge is that whatever decisions we make on which product to make, which resources to use, which processes to select for conversion of products, etc., have consequences. And these consequences can be represented by the energy, environment, water, food, health, nexus, or challenge. They are integrated, and this is even a bigger problem, thinking of a growing population on Earth, which requires an increase in the global GWP, increase in the production capacity of most commodities, which will require more energy, more electricity, more water, and which will increase the release of greenhouse gases. So the challenge, how to address the interactions of energy, water, food, health, etc., for a growing population. The third challenge is a little bit more complex. On the plot, you see the human development on the y-axis and the ecological footprint. On the x-axis, the vertical line, red line, indicates the Earth's biocapacity equal to 2.1 that was reported in 2008 from data from 2005. And this is related to the following numbers. Every country or region, for every country or region, the ecological footprint can be calculated, the biocapacity can be calculated. And what it means is that those that are green have the footprint bigger than the biocapacity, smaller than the biocapacity. That means their activities are less than the capacity for that region to endure. For the others, it is the opposite. And then the average now, 10 years later, that is 2018, the average was calculated to be 1.7. And you see that in the vertical dashed line. So in 10 years, we moved from 2.1 to 1.73. Who knows what will happen if we go to 0? So the third challenge is that how to avoid going to 0 by flattening the curve, which is in gray, to reach the curve which is green. This kind of analogy is very common, and now is very common with respect to the COVID-19 related pandemic. We need to flatten the curve to reduce the effect of the COVID-19. It's the same. We need to flatten the curve for global warming, for water, land contamination, forest destruction, loss of resources, and so on. That's the third challenge. So with these challenges, let us look at the opportunities. We have the opportunity that if we look at the current status of Earth, which is shown by the pictures, no need to describe them. What we want is to flatten the curve, obviously, and by flattening the curve, to achieve what is shown in the picture. So there are opportunities to do this, and we have to also see what actions are needed for the opportunities. The plot is on the left-hand side, shows the environmental impact on the y-axis and the economic profit on the x-axis. We certainly do not want this kind of situation, which will give us more profit and bigger environmental impact. What we want is this, where we get economic profit, but very low environmental impact. But this requires a new definition of the problem. We want non-trade-off solutions that decreases all environmental impacts, not just weighted sum, separately all of them, decreases the energy consumption, points to safer production, better economics, and all of these. A measure of whether we achieve more sustainable development alternatives is to consider as measure the Sustainable Development Goals. And there are 17 of these. Numbers 6, 7, 12, 13, for example, are very much related to what we can influence. So, opportunity for chemical, biochemical engineering and related disciplines to provide the means to find ways to flatten the curve to achieve some of these development goals. Also a question, are we actually targeting to achieve these goals in our different projects? Many of the published papers I see on sustainability do not actually refer to any of the goals that they have satisfied. So it's something to worry about. How do we measure the sustainability? We need to do the sustainability analysis. Here is a simple concept and the associated tools. We define the system in terms of our product, process, or both of them. Whatever comes into the system in the form of data, material, resources, money, people, whatever comes in, whatever goes out in terms of final results, as well as waste that is released and affecting the environment, and the waste that is recovered and reused. If we have all this information, there can be many ways to collect them, but whichever way we collect them and they are consistent and correct, we can then calculate the sustainability metric, for example, metric J, which are usually related to output and input, either the difference or the ratio. And the same information can also be used for models to calculate the carbon footprint, ecological footprint, and hydrogen footprint, and so on. So, and there are tools that are already available but the opportunity is to develop a systems approach for reliable and efficient calculation of these tools, of these measures. I will skip this slide. I think everybody knows what are the sustainability metrics and comparisons. So let me just skip this in the interest of time and discuss two scenarios that we will highlight. One is that we have the process. As usual, we convert our resources to the products we want, and that can also generate directly waste and CO2. But the process also needs, for example, energy, and that is provided by, for example, a power plant that converts energy resources, and depending on which resources they use, they will also generate CO2. So the process, as well as the power plant supplying the energy for the process, together will generate waste and CO2. There can be other ways to generate get the power from other energy sources that will not release energy, release CO2, for example. So what we can say is that there are energy demanding technologies like process A and energy producing technologies like the power plants. And they use different resources, some that generate CO2, others that do not. We need to combine those two in such a way that we will have zero or negative CO2. So opportunity to combine these technologies to determine new innovative solutions that are significantly better is possible. Scenario 2 deals mainly with pollution, where energy is not the important issue, but pollution in different forms and waste in different forms are important. And if we consider that nearly 95% of all manufactured goods rely on some form of industrial chemical processes, out of which nearly 500,000 chemical substances have been registered, and an estimated 40 to 60,000 industrial chemicals are found in commerce globally. And take into account that the measured data can be found for around 20,000 chemicals only. So what about the other remaining chemicals that we are using? What effect do they have? So opportunity to develop a system for prevention instead of curing the problem. Based on this background information, let's look at a systems approach that can provide the means to solve the problems. And we can revisit the multi-layered view of chemical engineering. What is coming from objectives from the left to the right, horizontal, is still the same. What is different are the means to achieve the results and achieve the objectives, to get the results to achieve the objectives. So the bottom to top, the underlined text is what is different. Now the core topics are modeling, synthesis design, operation control, planning and scheduling, numerical and computational aspects. These are the fundamental topics of process systems engineering that can help us to design, operate, analyze chemical biochemical processes, in addition to the fundamental chemical and biochemical engineering topics of thermodynamics, reaction engineering, etc. And again, we need to augment the fundamental topics with the topics from the middle and outer layers so that we can achieve the final goals. So develop methods to combine the core topics with those of middle and outer layers to meet the current and future challenges. So let us look at, since one of the core topics is models and modeling, let us look at how we can represent any system that we want to study with respect to synthesis design analysis issues. So what you see in the figure is a system That can be process, product, or both. There are information coming in. There are materials coming in. Also resources, material energy coming in, and information coming in, and information going out, and materials and energy going out. So if we have a model, then knowing what is coming in, we want to calculate what is going out. And this can be done at different scales by combining the models at different scales, starting from the lowest microscopic scale or phenomena to the largest mega scale, like enterprise. All of these can be handled through combination of different systems and models. And what kind of questions do we want to answer? Which material to use and how much to use, which product to make and how much to make. So there is decision variables as well as real variables. Which utilities, how many processing steps, and so on. So all of these questions we want to answer, and then if we answer them correctly, we will end up with a sustainable process design. So what we want to develop is generic methods, which are model-based representation of systems at different scales of size complexity, and we want to solve this for a wide range of problems. An example of what we can already do is the example of the use of a process simulator. You see a process flow sheet. This one is for ammonia production from air and natural gas. Ammonia is a very important product now because in addition to fertilizer manufacturing, it also can be used as hydrogen storage for hydrogen economy. So if we have the model through a process simulator, we can do the process simulation, we can do optimization control, process integration, analysis, and these problems are routinely solved, provided the needed information is available. You can think of that at any time on Earth, somebody somewhere is using a process simulator to solve this problem. So it's very common. But the question is, are all the information that is needed are available always? Let us look at a process simulator and the main parts of a process simulator. These are all available. But what happens if a process simulation flowsheet is not available? Or what happens if some model that we need is not available? Or there's a new unit operation? Or we need new solvents or catalysts or new compounds? Can the simulator work? Obviously, the simulator does not do these things. So we need a new class of simulators or software components. But we are still solving these problems. How do we solve this problem? Basically, we are doing a trial and error approach. We guess these things. Then we do the simulation. If they match our requirements, it's fine. If they don't match, we do again. The trial and error approach can give us the solution we need. We can be lucky if we can get it faster. But do we really get the order of magnitude improvement and new and novel solutions? In my view, no. So we need to develop a new class of component-based software tools associated with problem-specific workflows and data flows that can tackle a wide range of problems of interest. In order to do this, we need a generic model for the representation of system at whatever scale and at whatever complexity. So equation 1 is an objective function that can be multi-parametric optimization, but if we drop some of the terms and use them as constraints, it can be less complex. We need to define constraints on the process, like what is the product purity, that is equation 2. We need to balance for conservation of mass, energy, momentum, that is equation 3. That is actually the process model, which also includes the property model, that is equation 4. Then we need constraints on the process variable, like what is the upper limit of the pressure, the temperature, and so on. That is equation 5. We need to put constraints on the molecules that we will use, like solvents or catalysts. That is equation 6. And we can also define which connection between two processing steps through unit operations can be allowed or cannot be allowed. And that is equation 7. And with that, we can represent almost any problem we want to solve in chemical and biochemical engineering. And problems can be optimization of different types, simulation of different types, synthesis of different types, and so on. Depending on the equations, we can solve all the equations simultaneously. That would be direct solution. We can solve them in a decomposed manner. That would be decomposition-based solution, or we can do a hybrid, a combination of both. Which one to use and complexity? It will depend on how many equations we have, what is the complexity. It can be as simple as 7 equations which are linear, or as complex as 1 million equations and highly nonlinear. So the model and the problem will define the solution strategy. Here are some examples. Equations 4 and 6 typically represent a product design problem. Equations 2, 3, 5, 7, a process design problem. Equation 1 is the objective function if we want an optimal product or process. And any equations from process going to product or product going to process means an integrated product process design problem. If we solve only equation 3 or equations 1 to 3, we need a process simulator that also does optimization. But if we want to solve equations 4, 6 or 1, 4, 6, we need something similar to a process simulator we can call the product simulator. Or we can solve integrated product process, the simpler one, 3, 4, 6, or the most complex one from 1 to 7, and many more. So these are the types of problems we want to solve and the corresponding solution option that we need to have and the solver we need for them. So let's look at the decomposition-based solution strategy. We have 3 stages. We decompose the problem into 3 stages: the synthesis stage, the design stage, and the innovation stage. And this can be done through the 12 steps that are given in the workflow for sustainable process design. And in order to achieve this workflow, the different tools we need, the algorithms we need, the data we need are shown on the right. I'm not going to go through all of these now, but I will just point out one of the tools, which is this one. The other tool, ProCFD, is called computer-aided flowsheet design, which does all those other things. And you can point out, I can point out that where is the use of the simulator, as we know, is only with respect to simulation of the process, the rigorous simulation of the process on the top right-hand corner. Other than that, we need a lot of other tools that, unfortunately, the process simulator does not provide. So what is SuperRO? SuperRO is a synthesis tool that can do process synthesis as well as innovation, and it can be applied for both. So we define the problem in terms of what we want to convert and what we want to achieve. Based on that, we create a superstructure. SuperRO helps to generate the superstructure. Once the superstructure is generated, SuperRO converts this through the generalized model and represents the entire superstructure with the model. Then we do a model analysis to find out which variables and parameters need to be specified in order to solve the problem. We have a database that can help us to provide the variables for the known variables and parameters. Otherwise, we need to collect them and regress them. And once the model is ready to be solved, then we connect it to external solvers, and Super does this connection automatically, and it calls the numerical solver and then gives the solution. And then once the solution is obtained, we have a process flow sheet, which we can then connect to a simulator and do the simulation and optimization for the specific result that we have found. This gives us options for new innovative solutions that are significantly better and that can be generated. The final aspect of the tools and systematic method is representation of the result for comparison purposes. Sustainability, in my view, is not an absolute measure, it's a relative measure. So what we need is curves like the spider curve or the radar plot. The boundary, we have the green, which is the boundary, and what we want are solutions that are inside the boundary, and at least 2 of the vertices should be better than the boundary, and none of the vertices should go outside the boundary. If we achieve this, then we achieve the objective of sustainable generation of sustainable alternatives, and we have found them, and we can find them through new materials, through new equipment, through increased efficiency. With this background, let us look at some of the examples. The first one I will show is what we can do to reduce the energy demand. But energy demand is not enough. We also need to see, are those processes energy intensive? That means how much energy do they use? And compared to biochemical processes, petrochemical processes use more energy, and also the volume of the chemicals handled are much higher. In this specific example is a depropanizer, debutanizer, and the 2 columns, shaded columns, use a lot of energy. So, and they use distillation columns. So can we reduce the energy by replacing the distillation column, which is energy intensive? But I call it a long-term solution because at this moment, we do not have membranes that can directly replace a distillation column. But we can also have short-term solution because every day these columns are operating and releasing a lot of CO2. What we have found out is that instead of using distillation to go to 99%, which requires a lot of energy, if we go with the distillation only up to 95%, then 80% of the energy required can be saved. And instead of then going to 99% with distillation, we go from 95 to 99 with a membrane operation. But the membrane removes the higher boiling compound and not the lower boiling compound. So it's a small membrane operation. So we still reach the 99% requirement of purity, but we combine 2 unit operations that operate at their highest efficiency. Between 10 to 50% energy consumed by the single distillation column can be saved. Considering that at least 100,000 distillation columns are operating currently on Earth, there's an opportunity to make a big impact. Another one is that we have these 3 processes. All of them use reactor followed by separation. The bottom left-hand corner is a biochemical process. So whether it's a biochemical or chemical process, if the flow sheet is like this, reactor followed by separation, they can be converted into one intensified reactive distillation. The questions relate to the condenser and reboiler duty, as well as the number of stages in the reactive and non-reactive stages. But how do we know that for a chemical or biochemical process, a reactive distillation can be used and the required improvements can be achieved? If the answers that you see to the questions on the column below the reactive distillation, if all the answers are yes, then definitely a process can be converted into a reactive distillation. If a process for the separation part, the 7 questions are yes, then at least 2 columns can be converted into a divided wall column for the same benefit, at least 20% improvement. If a column is distillation column is operating and the answers are yes to the 7 questions, a hybrid distillation can be found with between 10 to 50% improvement, usually 20% improvement. So all of these are possible. And methods and tools are already available. Let's look at the synthesis design problem for a biochemical process, and it's multi-product, so it's not a single product biorefinery, but multi-product biorefinery. We have 3 raw materials: palm seeds, waste cooking oil, microalgae. We have biodiesel, which is P1, glycerol, which is P2, and other products which are P3, P4, P5. So how much product to make, which raw material to use, we want to find out by synthesizing the process and designing the process. So by solving this synthesis problem as a mixed integer nonlinear programming, we find out the detailed flow sheet of the process. And in order not to spend time on this, I simplified the description. So we have the biodiesel, we have glycerol, but we are not taking the biodiesel out from here. We take out from the green boxes that you see, because we take out part of the biodiesel and part of it we convert it to fatty alcohols, which have higher price than biodiesel. So when the price of biodiesel is low, we can convert the biodiesel to a higher value products. When it is high, we do not need to do that, or when the demand is high. At the same time, we have glycerol, whose demand is not very high, and we need to convert it to something else. And that I will show in another example where we can take this glycerol and do something else with it. So let's look at also the synthesis problem, because we already talked about that the Earth's resources are not uniformly distributed. So problems like this also are region dependent. So the first, we formulate the problem as a simple synthesis problem with 1 product, multiple raw material, 6 biomass raw material coming from 7 different countries. And we want to find out which raw material to use from which country to make ethanol with the best profit. But we also formulate, increase the superstructure information by dividing the superstructure into 4 parts: the raw material part, the product part, the pretreatment part, and the process part. And each of these parts can be done in each of the 7 countries. But without taking this information about the different locations and different countries, if we just take into account which are the raw materials from which country can be used to make the product at the highest profit, it comes out that the best is to use cassava rhizome to make ethanol in Thailand. However, if we take into account that different locations have different demands, different prices, different raw materials, all of these things, then the solution is totally different. The solution says that ship the raw material to Canada, use the pretreatment in Canada, and then use the processing of the pretreatment results in Mexico, and sell the product in USA because the demand and price is the highest in USA. But it does not take into account the transportation cost and the carbon footprint associated with it. If we take all those into account, the solution changes totally. The profit is less now, but the solution says that use the wheat straw available in Canada to do the pre-treatment, to do the production, and sell it in USA because the demand and price is higher. What about if we still want to use cassava rhizome and production in Thailand? Then it says, yes, you can do that and sell the product in India because the demand is higher in India, production is higher, the transportation cost is included, but the profit is much lower. So different scenarios can be formulated, and for different locations, different solutions can be found. And this is also interesting because it is not just a question of finding a solution, also finding the solution which is corresponding to the location where this would be applied. The last two examples are related to capturing of CO2 and making sure that the overall process makes profit as well as reduces the CO2 emission, as well as other options. So we capture the CO2 and then we convert the CO2 together with the raw material into the product. So we are integrating energy demanding technologies with energy producing technologies to find new innovative solutions that are significantly better. I will show the first example with capturing the CO2, then converting the CO2, utilizing the CO2 to convert and make different products. The figure shows DME. We can also make dimethyl ether. We can also make dimethyl carbonate, succinic acid, and so on. If we compare the results, if you look at the bottom row, the global CO2 reduction is negative, very good. But if we look at the net CO2 in terms of ratio of tons of CO2 divided by the tons of product, these are very small numbers. It's very good that they are negative, but they're still quite small. And the reason for that, I will tell you, but because they are very small, it means that the impact on global warming potential is very low. And the reason for that is that there are more CO2 atoms in the captured CO2 than the number of CO2 atoms in the DME, DCM, DMC, succinic acid, etc., that are produced. So these low carbon molecules is not, and the demand is low, so it's not helping us, even though we have very good solution. So what can help us is that if we do an enterprise-wide integration, that is enterprise-wide network, we include the process, the manufacturing process, but we also want to include the conversion process for energy, conversion process for water, capture all the CO2 that the conversion process will generate and use them so that the net CO2 will be negative or zero. So in that way, we can formulate the process, determine design of a sustainable network with net negative or zero CO2 emission that is economically feasible, safe to operate, and so on. Can this be done? In the reference papers, we have already pointed out that this can be done with biomass plus CO2 conversion of xylitol, and we can achieve economic feasibility, net CO2 zero emission, safe operation, and so on. But I will not go through the details of that, but I will use my last example to show another example where the synthesis problem is taking the glycerol or glucose from bioethanol plant or biodiesel plant and or use maltose and sucrose to convert them to succinic acid. And literature, fermentation processes can be found for 10 different ways to convert these raw materials into succinic acid. And after fermentation are the separation steps. There are 6 processes that are operating, and these can be found in the superstructure that I'm showing. But we also found 3 new alternatives that are better than the 5 that already exist. And one of those 5 is this flow sheet. We design this process, then we find out the weak points of this process to further improve. We set the design targets, then we solve the innovation process problem, and we find the final flow sheet, which is this, and there are other alternatives to it. And then we represent the alternatives in terms of the boundary and the alternatives that are inside. So these are true sustainable process design alternatives. Finally, I want to end with perspectives and conclusions. It's a busy slide. I will not go into the details of it. What I would just indicate is reality, which is experiment-based. This needs to be combined with virtual reality, which is model-based, and a combination of these to find the final result, confirm the final result in the shortest time, that is at the reduced cost and shortest time is what we want to achieve. And this can be achieved through an integrated approach. The virtual reality will find the solution very fast, and then the reality would do the experiments to confirm the solution of the virtual reality. Also, as perspectives, I want to highlight that we want to achieve circular economy objectives. Total circularity cannot be achieved because of thermodynamic limitations, but whatever can be achieved in terms of resources, in terms of services, in terms of products, we will achieve them. How we will achieve them? By increasing the time horizon of availability of resources and products, or by replacing one resource or technology with another. So both can be done. The means would be integrated experiment and model-based approach, unification of methods and tools, integration of energy, engineering and science, and also using augmented PSC techniques, that is machine learning, AI, and so on, together with the core topics. And more research is necessary in this area. Finally, I want to end with the role of chemical and biochemical engineers. So one is to promote research and development. I will not read out everything. Another one is to facilitate global dissemination, promote conservation and care of global resources, health, safety, and the environment, promote the highest standards of professional ethics and conduct for chemical and biochemical engineers worldwide, and to safeguard the public. Finally, prepare also for the next pandemic or disaster with methods and tools that can contribute to quick problem solution. That is, contribute to achieve sustainable development and influence the decision makers. With that, I end my talk, and thank you for your interest in the topic, and I will answer any questions you have.